given a parallel plate capacitor with an area of 3 centimeters squared, which I write in meters, so it's 3 times 10 to the minus 4 meters squared. Got my squared. Let me write that there. Okay, and the distance here between the capacitors is 0.5 times 10 to the minus 3 meters. It's hooked up to a battery that's 12 volts and it's fully charged. And then epsilon naught, of course, is just the constant, which is the permittivity of free space there. So for part A, to find the charge, we can use the fact that Q is equal to the capacitance C times the voltage being supplied V. So this is part A. Well, the capacitance is equal to the area divided by the distance between the capacitors. Okay, and then there's an epsilon naught here, so this is multiplied by epsilon naught. So that's the capacitance, and then this is still multiplied by V. So plugging in all those values into this expression, we find that this is equal to 6.39. So 39 times 10 to the minus 11. And the units here are coulombs. And we can box that in as our solution for part A. Okay, so now moving on to part B. So the charge here for part B that we're told to find is when the plates are now pulled apart to a separate distance of 0.75 millimeters. Okay, but the charge is not going to change. Since the capacitor is not connected to a battery, no charge can flow to it or from it. So the charge again, Q, is going to be equal to, same thing as in part A, 6.39. It's supposed to be decimal place there, times 10 to the minus 11 coulomb. And box that in. Is our solution for part B. We get a new page here for part C. Okay, so here for part C, the separation distance was multiplied by a factor of 1.5, right? To go from a distance, from the original distance of 0.5 millimeters to 0.75 millimeters, that's a 1.5 times increase. So the capacitance is inversely proportional to the separation distance. So the capacitance here is divided by a factor of 1.5. Since Q, the charge, is equal to the capacitance times the voltage, if the charge does not change and the capacitance is divided by a factor of 1.5, then the voltage must have increased by a factor of 1.5. Okay, so therefore the new voltage, we're going to call it V final, is going to be equal to 1.5 times the initial voltage we had, VI. We'll just call it VI here, but that initial voltage was the 12 volts. So 1.5 times 12 volts is 18 volts. We can box that in as our solution for C. Okay, so part D. Part D here, we're asked to find the work. The work is done in the change in energy stored in the capacitor. So work is equal to the change in energy. And this is potential energy, so we're going to call it delta U here. U is for potential. This is equal to 1/2 Q times the final voltage, so that's our final potential, minus 1/2 Q times the initial voltage we had, which was the 12 volts. So we'll just call it VI again. So plugging all those values into this expression, we find that this is equal to 1.9 times 10 to the minus 10. And the units here are the units of work, so it's joules. And we can box that in as a solution